Welcome. Let's take a look at evaluating a definite integral using the substitution strategy. In this case, we have the integral from 3 to 5 of x times the square root of x squared minus 9. And as we think about implementing the substitution strategy, we often look for a couple of features. One is there an composition of functions that can help us within the problem? Or is there the presence of two factors, if you will, where one is the derivative of the other? Well, in this particular case, I see a composition of functions. I see x squared minus 9 under my square root rather than just square root of x. Also helpful is if I think about taking the square derivative of x squared minus 9, I get 2x, and outside my square root function is an x function, x variable that could be helpful. So let's go ahead and take a look at this. So let's go with our first intuition and let u equal x squared minus 9. Then du is u prime of x dx. So du is 2x dx. Now, as I look at my integral here, I see that I have x and dx, but then I'm missing the 2. So let's go ahead and multiply by 2 and by 1/2. 2 times 1/2 is 1, so we haven't changed the value of this definite integral at all. So right now we have 1/2, the integral from 3 to 5, and I'm going to write the square root function part first, so square root of x squared minus 9, and then using the commutative property of multiplication, we'll go ahead and write the 2x second dx. And so now what I have is I can clearly see where my du is going to be. I'll be replacing this 2x dx with du. I can clearly see where my u is going to be relevant. I'm going to replace this square root of x squared minus 9 with square root of u. I have one more detail, though, I need to attend to. That is that these limits of integration are values of x, and we're transforming our integral from one being described in terms of x to a equivalent integral in which we're describing with a variable called u. The values of the two integrals are the same. And if we thought about this as area under the curve, the area under the integrand, between the integrand and the x-axis, would be the same. So let's go ahead and transform our limits of integration as well. So my upper limit of integration was 5. So my new upper limit of integration is going to be 5 squared minus 9. Well, 5 squared minus 9, 25 minus 9 is 16. So 16 is my new upper limit of integration. My lower limit of integration started out as 3. We're transforming it now. So my new limit of integration is u equals 3 squared minus 9. Well, 3 squared minus 9 is 9 minus 9, so that new lower limit of integration is 0. So I have an entirely new integral. I have 1/2. My new lower limit of integration is 0. My new upper limit of integration is 16. I have square root of u as my integrand and du as my differential. Almost ready to evaluate that. I'm just going to take the extra step to rewrite my square root of u as u to the 1/2 power. Now that I've done that, we can go ahead and evaluate this integral. We'll have 1/2 times. Now the antiderivative of u is u to the 1/2 plus 1. So 1/2 plus 1 is 3/2. If we divide by 3/2, that's the same as multiplying by 2/3. So I'm going to go ahead and multiply by 2/3. And then we want to evaluate that from u equals 0 to u equals 16. Notice that this 1/2 and this 2 in the numerator of 2/3, they can simplify a little bit, and we can start substituting in the upper limit of integration. So I have 1/3 times 16 to the 3/2 power minus 1/3, 0 to the 3/2 power. Well, 0 to any power other than 0 is 0, so this is all 0. And let's talk about what 16 to the 3/2 power is. So 16 to the 3/2 power, recall, is the same as saying, let's take the square root of 16 and cube it. Square root of 16 is 4. And 4 cubed is 64. So the value of this integral is 64/3. I hope you find this helpful.